lecture we will be talking about electron diffraction pattern. Now, before going into this electron diffraction, let us first recapitulate how a real optical lens works. So, consider a real lens of glass. So, it is basically you have this is where you keep a sample, and this is your lens, and you get this is where you get the image. So the light rays actually from the sample they fall onto the lens. Right, and this is the place you get the image. And the diffraction plane is actually, this is where diffraction might take place. Now taking the analogy of this real lens, if you go to the crystal where we have atomic planes, so if this you consider as atomic planes with the atoms, so and when you allow an electron beam to fall on these atomic planes, so they also get diffracted, and if this angle is theta, similar to the Bragg's law, diffraction will occur when 2d sine theta is equal to n lambda. This condition is satisfied. Now, if we draw the Ewald sphere, so what is an actual Ewald sphere? So this is your sample, and this is say one of the HKL planes of the sample, and you are allowing an electron beam to fall onto this. So in the reciprocal lattice, it will look something like this. So electron diffraction is taking place at an angle, say 2 theta. This is your HKL plane, and this is the origin of the reciprocal lattice. And this is the first diffraction spot, and so we call it as PHKL, this point, and since this is a reciprocal lattice, so this length will be 1 by lambda. Lambda is the wavelength of the electron beam, and this is the GHKL or reciprocal lattice vector. Okay, so according to the diffraction conditions, the reciprocal lattice points should be on the surface of the Ewald sphere. So this is what is happening here, and the distance between the two is the reciprocal lattice vector. Now, if we would like to understand what is the relationship between the different parameters when you have electron diffraction pattern that is called an SAED pattern, and we get in TEM. Apart from the microstructure, we also get an SAED pattern. So what is the relationship between the different instrumentation parameters and the reciprocal lattice, that is the diffraction spot that we have obtained? So considering the Ewald sphere only, we take an example. So if this is the Ewald sphere, say this is the sample, and this is the Ewald sphere. Now we know that if we have a very large radius, so the curvature of the Ewald sphere starts to get minimized, so we consider it as a straight line. So this distance is again 1 by lambda. This is again the origin. Sorry. This is again the origin. Got it as O. And so a diffraction. This is the first diffraction spot. Now, if we take this to the TEM screen, where actually we obtain the electron diffraction spot by using a fluorescence screen. So this is where we have obtained the diffraction spot, and we take this N1 as R. That means from the center of the diffraction spot, from the origin of the diffraction spot to the first diffraction spot, we would take it as R. And this distance is again your reciprocal lattice G, and this distance from the specimen to the camera, we call it as camera, so this becomes your camera length L. So we have camera length 1 by lambda, distance between the central spot of the diffraction pattern to the first diffraction spot, and you have got the G, that is the reciprocal lattice vector, that is distance between the origin of the reciprocal lattice and the point where the first diffraction spot is in the Ewald sphere. Okay. So now from basic proportionality theorem, that is, if we have a triangle like this, say this is your triangle, sorry, if you have a triangle like this, so you have got say this is A, this is B, C, this is D, and this is E. So it says that AB by AD is equal to BC by DE. It means the ratio of this distance to this distance is proportional to the ratio of this distance to this distance. Now, the same thing we could apply in the electron microscope configuration. Then this is your so this is R. If you could remember, this is your R. Right. If you could go to the previous diagram, you can see this was your R. This was your G. This is 1 by lambda, and this is 1 by L. So again, so this is R. This is L. This is 1 by lambda, and this is your G. So it becomes 1 by lambda, that is AB, divided by AD, that is L, is equal to BC, that is G, and D, that is R. Now this reciprocal lattice vector is equal to 1 by D. Rather, we could put it 1 GHKL is equal to 1 by D HKL. So D is the interplanar spacing of the atomic planes. So upon simplification, we obtain R D is equal to L lambda, and this is the equation which is used in analyzing the diffraction spots obtained in a diffraction pattern. Now this L lambda, so let us consider, put on the slide. So we have RD is equal to L lambda. Now this L lambda is sometimes called camera constant. Actually, when we obtain a diffraction spot on the fluorescence screen of a TEM microscope, it actually gets converted into the computer screen, okay, where we are watching it. Now this conversion, this actually due to this conversion, an extra constant gets added here, right, which is around, say, 5.7. So this is the magnification factor. So usually you can call L lambda may be considered to be as a common constant, but there is also a multiplication factor associated with it, which is usually 5.7. Now, while let's consider the different diffraction patterns that we obtain in a saed pattern. So if we have a polycrystal, we usually observe a ring pattern. If you have a single crystal, you obtain a spot pattern, parallel lines containing spots. And if it is an amorphous material or a nanocrystalline material, for that matter, you get a halo pattern. That means it's something like this. Let's consider it as, so we get, sorry. It is instead of definite crystallographic lines, these lines would be like this halo sort of thing. You see that there are circular shapes, but you would not be able to identify any particular lines. It would be like bands. Okay, so this is how this amorphous diffraction pattern looks like. Okay. Now, coming to the single crystal patterns. So, say you have this is your specimen and this is your revolved sphere. So, we have a single crystal patterns, as you have seen. This is basically the spot pattern. So, this is a revolved sphere, we call it EW sphere. And this is your specimen. And so for each diffraction spot means that it is corresponds to one diffraction plane. So this is one plane, this is one plane, this is another plane. Okay, and the central line is called the zone axis. Now, if we name, say, one of the planes as H1, K1, L1, and another one as, say, H2, K2, L2, so the zone axis is actually the cross product of H1, K1, L1 and H2, K2, L2. So a plane is always considered or always named by its normal. So if I consider H1, K1, L1, so it is the normal of the plane which I am considering. So this normal into this normal gives you the zone axis B. Okay, so this all diffraction spots from plane, they actually belong to one zone. So that is how this zone axis comes. And in the case of a polycrystalline material, what happens is that, say this is the specimen, each one of them will create a cone, a solid angle cone. Each of the diffraction, each of the crystal, each of the phases, each of the planes will create a solid angle of its own, like this. So that is how, if you take the two-dimensional representation of these cones, so you get a concentric circles. So these concentric circles are actually base of the solid cones that have been formed by each of the atomic planes. So that's how you get a ring pattern in a polycrystalline sample. So it's ring pattern polycrystalline sample and a spot pattern in single crystal samples. Now this ring pattern can be actually analyzed by the equation that we have just derived, that is RT is equal to L lambda. So this is the center. So this R is the first radius or the radius of the circles. So, and we know what is the camera length and what is the lambda. So from this equation what we get is this D. So we have, say we have 5 circles or we have 3 circles. So R1, R2 and R3 will fetch us D1, D2 and D3. Now using these interplanar spacings and from the GCPDS, we actually find out what are the HKL planes associated with this. So H1K1L1, H2K2L2, and H3K3 and L3. So corresponding to the three rings, we have got three different phases of the polycrystalline material.